Welcome to lesson 9.2, Prisms and Cylinders. So before I get into this video lesson, just like the last lesson we went over, after going through the video and the notes saying that this lesson is so heavy in vocabulary and understanding the relationship between these vocabulary terms, I'd highly recommend taking a few minutes to read through the book lesson that I summarize in these notes videos, just to make sure you get the full understanding. In the book, you'll see some helpful pieces about being able to draw cylindrical solids with different types of leans. I'll also attach a video helping you with that process. So beginning with prisms and cylinders, we first need to think about what is a surface. So a surface is a three-dimensional figure that separates space into two regions. So three-dimensional figure is a surface that separates space into two regions. A solid is the union of a surface and its interior. So a surface and its interior makes up what we call a three-dimensional solid. For example, a balloon is the surface, while a bowling ball is a solid, meaning the balloon is just the latex or the material filled with space in between, where the bowling ball, it's solid to the core, so the bowling ball includes the surface and the interior. When drawing, you can distinguish a solid from a surface by shading and showing no hidden lines. Then we have a few other pieces to make sense of. We have a face. A face is a polygonal region, and in this example to the right, ABCD would be a face. So ABCD would be a face of that solid. The edge would be the segment joining two faces. So AB, the segment here, is an edge because it joins this front face, DCBA, and the bottom ABE or ABFE. And then we have vertices, which is the endpoint of a segment or an edge. So for example, here, point A would be a vertex, B is a vertex, F is a vertex, E is a vertex, and so on. So just some general vocabulary pieces. So that idea of surface and solid then builds into our definitions here in this box. A cylindrical solid is the set of points between a region and its translation image in space. So if I took AEFB here and translated it up and to the right to DCGH, then the cylindrical solid would be everything in between those two images. The pre-image down here and the image up there. The boundary of the solid is called the cylindrical surface. So our boundary of the solid is the surface. So making more sense of that, breaking it down, in a cylindrical solid, the region that was translated and its image are the bases. Bases are always congruent and are always parallel planes. So like here, ABFE and DCGH are parallel and congruent. The rest of the surface of the solid is called the lateral surface. So if it's not the bases and it's on the surface, we would call it the lateral surface. When the bases are polygons, the lateral surface is made up of what are known as lateral faces. So if our bases are any sort of polygon, our lateral surface will be called lateral faces. The intersection of two lateral faces is called the lateral edge. The height or the altitude of the solid is the distance between the planes of its bases. And then when lateral edges are perpendicular to the bases, we say that it is a right solid. If we have any other relationship between the lateral edges and the bases that are not 90 degrees, it's known as an oblique solid. So oblique would mean it's leaning any way other than 90 degrees. So, taking this paragraph and applying some of the vocabulary. So the surface at the right here is made up of 6 rectangles and 2 regular hexagons. So the hexagon on top here, hexagon on bottom, would be our bases. All the rectangles would be our lateral faces, and a lateral edge would be an edge in between our faces. So identify a base. So one base on this figure would be hexagon A, B, C, D, E, F. The hexagon around the top here. That would be a base. A lateral face could be rectangle AFPQ, rectangle right here. Or you could have gone FEOP. And then a lateral edge, DN, or we could have gone EO, FP, AQ. Lateral edge would be any of the edges that connect our lateral faces or in between lateral faces. And then, because the lateral edges are perpendicular to the base, this would be a right figure. If it was leaning, then it would be an oblique figure. So if this whole thing was shifted over here, so it looked like it was leaning one way or the other, it would be oblique. So then we get into our main idea, the definition of a cylinder or a prism. So a cylinder is a cylindrical surface whose base is a circle. So if we have a cylindrical surface, which we look up here, our different cylindrical surface would be the boundary of any cylindrical solid. So a cylinder is a cylindrical surface whose base is a circle. A prism is any other cylindrical surface whose base is any sort of polygon. So if the base is a triangle, a square, a rectangle, a hexagon, an octagon, a pentagon, a decagon, etc., it would be a prism. If the base is a circle and it's a cylindrical solid, we have a cylinder. So then we get into some more info on prisms. Prisms are named by the shape of their base. For instance, if our base is a triangle, the prism's called a triangular prism. The faces of the lateral surface of a prism are always parallelograms. A regular prism is a right prism, so a key here is that it has to be right, whose bases are regular polygons. And then we get our cube, which a cube is a special type of right square prism where all 6 faces are congruent squares. So trying to organize all these different pieces, vocabulary terms, etc., we're back to that idea of a hierarchy. So we know as we move down the hierarchy, things get more specific. So our most general term would be a cylindrical surface. That then splits to either a cylinder or a prism. If it's a cylinder, we know the base is a circle, and we only have 2 options. It's either a right cylinder or an oblique cylinder. If we have a prism, we also have that option of oblique prism, and that branch stops there. Or if it's a right prism, that then can split to a regular prism or what we could consider some sort of box, what we might call a rectangular prism. So a box here could also be called a rectangular prism. And then if we have a rectangular prism that's also regular, meaning all four sides are the same, that would create a cube. So next to box here, feel free to put AKA rectangular prism. Now we get into example 2 here. It says, in the figure below, ABF is a translation image in space of DCE. So that means DCE was translated to create ABF. So what's the general name for the figure created? This whole figure here, we would call a cylindrical solid. That's the general name. Name of the bases, well, our base shape are triangles. So we'd have triangle AFB and triangle DEC. Because our bases are triangles, we would have a triangular prism. And then the lateral faces would be our sides in between our bases. So here we'd have parallelogram AFED. We would have FBCE. And then we'd have ABCD. So we have three different faces. And the edges would be any of these seams or parts, segments, where our faces meet. So we'd have segment AF, FB, BA, DE, EC, CD, AD, FE, and BC. All of those are different edges. And then we get to our last example for this lesson. Example 3 tells me I have a right cylinder pictured at the right. And the key here, why it matters that it's a right cylinder, is I have the right angle here that eventually allows me to use this right triangle. But the right cylinder has a height of 10 centimeters. So the distance in between our base circles is 10 centimeters. So right here would be 10 centimeters, same with down here. And we know the base area of the circle is 25 pi centimeters squared. They want us to find this diagonal of the cylinder, PQ. So how do we do this? Well, right away we know segment, if I would label this from P to this point on the circle, I'm just going to label it R. So segment PR here would be the diameter of the circle, but it's also the leg of the right triangle PRQ. So we're going to use the area of a circle to figure out this distance PR. So first, I know area of a circle is pi times the radius squared. So if my circle area was 25 pi, I can divide out the pi on each side. So 25 would equal r squared. Square root of 25 is 5. So I know the radius of this circle is 5, telling me the segment PR, that diameter, would be 10 centimeters. So now I have a right triangle, PRQ, where PR is 10 and RQ is 10. So PQ is the hypotenuse of that right triangle. So we'll use Pythagorean theorem, a squared plus b squared equals c squared, to find that distance of PQ. So 10 squared plus 10 squared would equal x squared. So 200 is x squared, meaning x is the square root of 200, which simplifies to the square root of 100 times the square root of 2, and the square root of 100 is 10. So that distance for PQ would be 10 square roots of 2, or approximately 14.14 centimeters. So again, these examples aren't exactly everything related to the lesson, so I'd encourage you to go back through, read through the lesson and the other examples, and then I'll also include an additional video about trying to draw these figures with different degree leans.